To start by thanking the organizers for inviting me to talk at this marvelous conference. I am also happy I am not the very last speaker, so I can enjoy the rest of the conference after my talk. I will be talking about Bootstrap, present and future, and well, you will see. So my style will be a bit different from the rest, from the previous talk. Sorry. Good. So the philosophy of the Bootstrap is to bound the space of consistent theories by imposing a minimal set of general principles. By imposing a minimal set of general principles or consistency conditions on a given set of observables. And the plan of my talk is first I will review or I will remind which kind of typical questions one can ask in the Bootstrap context. And then we can address the question, and I will, again, as Nati, address a single question. What can the Bootstrap teach us about string theory or quantum gravity? And the second part of the talk will be about the future, and the first part of the talk will be to the future, because will be mostly for young people here. So it will be very basic for most of you. Now, I have to do a disclaimer, so this is a beautiful and vast subject, and it has been developed by many, many people, and this is not a review, so I may miss some very important developments. Now, and the first thing I did when I was invited to give this talk was to type Bootstrap in Google to see what Bootstrap was. And the first thing that appears, if you do that, is the so-called S-matrix Bootstrap. And the simplest setup to understand the S-matrix Bootstrap is to focus in the 2-to-2 scattering of the lightest particle in a gap or massive Lorentz invariant QFT in 1+1 dimensions. So that's a super simple problem. And in this case, if you're in 1+1 dimensions, the three Mandelstam variables are not independent of each other. They all depend on the single Mandelstam variable S. And then you can write the S matrix S as a function of this little s. Now, the physical region corresponds to values of the Mandelstam variables bigger or equal than 4m squared. But it is a very good idea to try to extend this to a complex variable. You say now S is complex, and then you extend the S matrix to an analytic function in the complex S-plane. And then in this context, you ask for this analytic function to have a few properties, and these are the general principles in this case. So first, you require analyticity. Then you require the fact that this function S has to be crossing symmetric, because we are scattering identical particles. Then we have unitarity, because the absolute value of square of S is a probability, basically, and probabilities cannot be higher than 100%, unfortunately. And then we have to say something about the analytic structure of this analytic function in the S-plane. And a very common thing to require, for instance, is that this matrix S, it will have two branch cuts starting at the threshold here, and this is just the mirror image under crossing. And then we can say, for instance, that if these two particles of mass little m produce another particle of big mass m, that will be seen as a pole of this S matrix. And the question we can ask is how large can this G squared be? And notice that this is a question that you can ask completely regardless of what the Lagrangian of the theory is. And this will be a typical feature of Bootstrap. We don't care about the Lagrangian of the theory or if the theory has a Lagrangian or not. And it turns out that actually, if the question is how big this residue is, you can actually answer this question. And one of the lessons that you learn in doing that was that the beautiful thing is that actually complex analysis is very powerful. This has been known to people working in particle physics for decades, and now we are seeing again and again how powerful really complex analysis is. And a beautiful property of complex analysis is that the smart people like Cauchy has studied it and developed that for many years. So for instance, using the Cauchy theorem, you can find a dispersion relation. So you can write down the value of S at a point S as a given by this contour integral, and then you can deform the contour and write the same as a real integral of the discontinuity of this function S. And this is quite cool, actually. The fact that just given the discontinuity of this function S, you can find the function S in the whole complex plane. An important little point I would like to make, we have made an assumption that S decays at infinity, because in going from here to here, we have thrown all the contribution of the arcs at infinity. So this is the simplest setup for the so-called S-matrix bootstrap. Another entry that you will get in Google is the so-called modular bootstrap, and we have seen a little bit in the talks by Dalimil. And in this case, the setup is to focus in the partition function of a two-dimensional unitary CFT on the Euclidean torus. And again, in that case, you define a function set of tau and tau star, where tau and tau star are complex conjugate of each other, but very much like what we did before, it is now very convenient to think of tau and tau bar now as two independent functions, and we think, and actually one can prove, that this partition function is holomorphic in the upper half plane here and the lower half plane there. In this case, so this is the observable. In this case, the general principles are first that this set is the sum over characters of whatever symmetry you are considering, let's say Virasoro symmetry. Then unitarity implies, for instance, that these H and H bars cannot be negative. And then, if you are studying the theory on a torus and you go to equivalent tori, the partition function should not change. So this function should also satisfy modular invariance. And the type of questions that you ask here in this context is how large can H plus H bar, the dimension, of the first operator after the identity be? And this, again, is a question that you can answer without any reference to the Lagrangian of the theory, etc., just following this very basic set of principles. Then we have the conformal bootstrap, and in the conformal bootstrap, the quantity to study is the correlator of four identical scalar operators in a unitary conformal field theory in d dimensions. So here we have this 4-point function, and now the general principles, again, no reference to Lagrangian. So the general principles are that because of conformal symmetry, this function g has to decompose into conformal blocks, exactly as shown here. And if we are studying a unitary conformal field theory, we know that these ones that come from the square of the OP coefficients, they have to be some positive, some non-negative coefficients. And in addition, we know that the dimension of the intermediate operators has to be above some unitarity bound, so bigger or equal than unitarity bound. Now, in the simplest setup, again, we are considering the 4-point function of 4-point correlators, so you should be able to exchange any two of those, and this implies this crossing symmetry equation, and well, which in terms of this cross ratio set is basically given by this. So this one corresponds to exchanging 1 and 3. Notice, by the way, the similarity with all other problems, basically. So you consider an observable, then the observable, you can expand it in terms of something, thanks to the symmetry. Then the coefficients in that expansion are always positive because of unitarity, and then you have crossing symmetry, modular invariance. So actually, the three problems look very much the same. Now, in the case of the conformal bootstrap, what is a typical question that one would ask? So the typical question is the following. If we consider the operator product expansion of the external of two of these external operators, that conformal, that OP expansion will have always the identity operator, the stress tensor, if you are assuming that the theory is conformal, and then some tower of intermediate operators. And basically, the question now is to try to constrain the dimensions and OP coefficients of these intermediate operators. And the beautiful thing of the conformal bootstrap has been to prove that to satisfy all these constraints is highly non-trivial, and in particular, that implies serious consequences for these coefficients and also for the dimensions of what the intermediate operators can be. Again, in this context, it has been proven very nice to think of set and set bar as actually complex coordinates independent of each other. So if you are considering a Euclidean correlator, again, set and set bar would be complex conjugate of each other, but it is very nice to consider correlators in the Laurentian signature, or say that they are complex and independent. And again, playing with complex analysis, we can actually find a Laurentian inversion formula that is very similar. It can be thought of as a dispersion relation for a conformal field theory. So notice the similarity between this relation here for the CFT data and this relation that we have just derived using Cauchy. If you want to be a bit more precise, this is more analogous to what is called the Frost-Gribov, which is equivalent to what I just wrote before. And again, boundedness, in this case, for the correlator at infinity, etc., it is quite important. Now, a beautiful thing about this formula is that this formula shows that the CFT data is manifestly analytic in the spin. And what that led to, and we have seen a talk 2 days ago, is that there exist non-local operators, they are called Lie-Right operators, that correspond to generic J here. So if here J is 2, 4, etc., then you get a nice usual operator. If J is a square root of 2, you get a non-local operator, but however, it is an operator that exists in the CFT. Now, I have to say, mostly other people have actually made remarkable progress, analytic and numerically, on these 3 unrelated areas. Now, since this is not a review, I don't have to review that. And so we will focus in a single question. And that question will be, what can the bootstrap teach us about string theory or quantum gravity? So the first question, which is a question that makes connection with the talk by Nati, is actually the following. Imagine that you have a low-energy effective action which someone tells you arises from a UV complete theory. You don't know what the UV complete theory is, but you just know that it arises from a UV complete theory. The question, the natural question then, is what are the constraints imposed by the bootstrap? And the kind of constraints that we may see may be constraints on this coefficient, in the coefficients in front of the relevant operators, but irrelevant operators, but they may also be the fact that you need to add extra degrees of freedom, extra matter, etc. And this is a very interesting question. For instance, Nima and collaborators, they have studied causality constraints, and those imply a specific sign for this lambda 3. And in order to attack these questions from the point of view of the bootstrap, one has 2 obvious strategies. For instance, one strategy would be that if I give you the effective action, for instance, you have just this with all the coefficients, then you take the effective action, and from it, you compute the S matrix, you compute scattering amplitudes, and then you check whether these scattering amplitudes satisfy all the conditions that I gave in the first part of the talk. And recently, there has been a beautiful 1+1 example constraining the flux tube effective action by these people here. And this is an example of how this strategy works in a very nice, but very simple and nice example. Then there is a second strategy, and the second strategy is hinted at by the EDS-CFT duality. Imagine that you want to study a theory in EDS. You want to know whether a theory in EDS is a consistent theory. Then what you could do is to take your scattering in EDS and map that scattering in EDS to a correlator in the boundary. And then what we will say is that we will apply the conformal bootstrap to the boundary theory. And one can say the following. One can say that a theory in EDS is consistent, or an effective theory in EDS is consistent, if the theory on the boundary satisfies all the bootstrap constraints. And this is another way in which one can, in principle, study theories. You can both study theories in EDS or take the flat space limit and make a connection with the previous strategy. If you want to see whether a theory admits a UV completion, etc., I think the most interesting example, certainly for this conference, are UV complete theories of gravity. Now, we know that pure gravity, at least in 4 dimensions, is not a consistent theory, it's non-renormalizable at 2 loops. So in some way, we have to UV complete it. So there has been many approaches. So here there is a Gauss-Bonnet term, there is like a Lovelock, etc. So you can add all kind of, sorry, the word crap comes to me, but that's not very nice. So you can add a lot of things, and you can complete gravity. And then you can ask, what is the most general consistent completion that you can have? And a very nice example of how the bootstrap could be used for that came from the talk by Shiboevov. And in that case, either by studying amplitudes for shock waves, so following a strategy similar to one, or by studying the conformal bootstrap for light operators, one can actually show that this, for instance, something like just Gauss-Bonnet without extra degrees of freedom is not something consistent. So I think it would be really nice, and now I will talk more about this, to try to follow this direction even more, because as a string theorist, that is what we want to see. But I will come back to this later. Notice that for gravity on EDS3, we have a CFT dual that is 2-dimensional, so we can use the power of modular bootstrap, and as we have seen in this talk, this modular bootstrap offers a beautiful tool to study whether, for instance, pure gravity in EDS is a consistent theory or not. Now, there is a very similar question if I give you an effective theory, and it's the question of the swampland versus the landscape. So if you have, actually from what I just said, I hope that you believe that the bootstrap seems the right tool to see whether a nicely looking effective field theory belongs either to the swampland or to the landscape. And this has not been exploited too much. I think the combination of bootstrap with landscape and swampland, but it's a very interesting direction that is starting now to be explored. But notice that the thing about the bootstrap is that the bootstrap gives only a set of necessary conditions. So basically, if we have an effective field theory, the effective field theory could belong to the swampland or could belong to the landscape, but in the best case scenario, when you do the bootstrap test, so to say, the theory will belong to the maybe land. So the maybe land is something like having some J1 visa for the landscape, but after a while you may have to leave the landscape. So something that we need to do, and I think we need, if we want to answer the question, these sort of questions with the Bootstrap is to try to improve the Bootstrap to give not only necessary conditions, but also sufficient conditions. And a few ideas that these, I think, are the directions in which people will make progress. Is also partly a wishful thinking, and partly is already happening. So the first condition is that when you study Bootstrap for a single correlator, that gives you very nice conditions, but these conditions are not a lot of them, right? I mean, it's just like passing one test in the university. You have all the other 30 tests to get your degree. So it is important to develop the conformal Bootstrap for operators with spin. I mean external operators with spin, and that is something that is already happening. Rather than studying correlator by correlator, it would be very nice if we could encode the Bootstrap conditions for an infinite number of 4-point correlators. For instance, in the numerical Bootstrap, it has been seen, for instance, for Ising, that if you consider a finite number of correlators, more than one, let's say, you shrink from regions to islands. But it's not clear whether these islands, you can make them points. And I think that in order to make them points, we will need to consider an infinite number of correlators, and we may think what is a smart way to consider infinite correlators. And an alternative to this, actually we discussed this with David Gross 2 years ago, is that instead of considering an infinite number of 4-point correlators, we could study higher point correlators of a single operator. And I think these, morally, will have the same amount of information as infinite 4-point correlators. Another thing in which we have to make progress is in studying the Bootstrap for non-local operators. So we have seen in this talk, and thanks to the work of Sasha, Harman, and other people, that to study Bootstrap for Lie ray or ANEC operators was just a super good idea. And actually, local operators in a conformal field theory are just a little subset of all the operators that you can consider. You can consider line defects, surface operators, combinations of them, and one could try to think how to try to develop a Bootstrap approach for these non-local operators. Another direction that I think would be very nice is to try to use Bootstrap in order to constrain gravitational physics or the physics of black holes. And a way to do that would be, for instance, to study some correlator or some observables where the external states are very heavy objects. And this, in the context of two-dimensional CFTs, has again been done, but not so much in higher, but there are some works in higher dimensions as well. And one thing that would be nice to understand in this circle of ideas is large N theories at finite temperature, for instance. And then there is a lot of very nice classical GR problems where it would be very nice to have some kind of like Bootstrap approach to these problems and be able to prove some of the classical theorems of GR. Now, a question you may ask is whether the Bootstrap can do this alone. I mean, there are some people who is like purists and they want to use only like Bootstrap ideas and that's it. Actually, the Bootstrap doesn't have to do it alone. So we know a lot of physics that has nothing to do with Bootstrap, or not much to do with Bootstrap, and these are all interesting physics. And actually, over the last years, we have been combining Bootstrap with other techniques, SUSY localization, integrability, EDS-CFT, for D2D dualities, and we have learned a lot about quantum field theory. And I very much hope that this mixture of Bootstrap with other ideas continues to happen, and it includes also ideas from GR. Going back to quantum gravity, so the question that I posed was the following. So we know that just the Einstein-Hilbert-Lagrangian by itself is not good, so we need to complete it in some way. And a very natural question that we can ask is the following. Is there a set of conditions a set of general principles that leads to a unique completion. It may be a very long set, it may be on weird observables, but is there a set such that the completion is unique, or there are only a few completions? And then once we have that, if we find it, there is a slim chance that this will happen to be true. We can ask whether this completion is local or non-local, whether we can take away cutoffs, whether it has a higher spin fundamental degrees of freedom, and more generally, whether it is a string theory. And if we do that, and if we find such set of conditions, we will finally have an answer to the question that is often asked in these vision talks. So the question is, what is a string theory? And the answer is the unique solution to Bootstrap with that set of conditions. Thank you very much.
Great. Okay, so there were a few interesting questions from the audience, and they, I think, wanted to ask whether you could apply the Bootstrap to answer interesting questions about holographic theories. For example.
Yeah. Shall I answer that? Or?
Well, specifically.
Yes.
Yeah. More than one question asked specifically. So, you know, our examples, supersymmetric for sure, examples of ADS-CFT have large internal dimensions. Can you use Bootstrap to construct an example with a hierarchy of scales? Or another question, which is in the same class, is can you use the Bootstrap to rule out ADS compactifications with a small internal manifold, thus putting into doubt the existence of the landscape?
Right. So, yes. So the obvious answer, well, there were many questions, all interconnected. So the first question is whether you can apply the Bootstrap in the context of the ADS-CFT duality. So here there are many levels to that question. So there is a very nice example, very neat example of the ADS-CFT duality, where the dual is n equals 4 super N mills, and we have n equals 4 super N mills on one side, tied to V superstring on ADS 5 cross S5 on the other side. And certainly something that you can do in that case is you can look at correlators of n equals 4 in a 1 over n expansion, and then you can apply all your Bootstrap constraints, and from the Bootstrap constraints, you can see how much of the features you can recover of strings on ADS 5 cross S5. And if you do that exercise, something that you can discover is that when you do this kind of computations here, but you take into account also the R-symmetry structure of n equals 4, then you recover what would be a 1 over n expansion, and actually also a low energy expansion of a string theory on ADS 5 cross S5. And that, at least, of course, we don't know amplitudes. So this was the subject of the talk by BC. So of course, we don't know what the amplitudes in ADS are, but you can take the flat space limit, and you can compare those with 10-dimensional amplitudes in flat space. So this is the first level of the question.
So the techniques are available.
So the techniques are available, but then you start to make some assumptions about the CFT, and then the more assumptions you do, the more can you get. And in that case, for instance, something that happens is that when you do if you go to genus 1 computation, you see that the dual has to have 10 dimensions. So some features of the 10, let's say, large dimensions. So some features like the dimensions, etc.
Specifically, part of, I think two of the questions were, what is it in the boundary conformal field theory that tells you that the internal dimensions have to be the same scale as the non-compact direction?
Absolutely. And if you go back, sorry, the answer was too long. So if you go back to the CFT. The CFT has a tower of protected operators that are there because of this SU4 symmetry, and that tower of protected operators with very specific 3-point functions implies that actually the dual has 10 dimensions. Now you can turn around the question and say, what can I say if the dual has 10 dimensions? What can I say about the CFT? And from the CFT point of view, there are some informations about 3-point couplings for operators with this large R charge that you can say, actually. Now, to rule out...
Can the Bootstrap be used to answer the question, do the compact
yes.
part of the 10 dimensions be of the same size, the same scale as the non-compact part?
I think that's hard at the moment, but I don't see why not in the future.
Okay. There's a very interesting question, which is really a research project for a young postdoc, posed by an anonymous member of our community, which is, can you imagine proving, very interesting question, can you imagine proving that there are no interacting CFTs in large, actually, the way he phrased it was asymptotically large dimensions using the Bootstrap?
Right.
Something we all believe.
Yeah, no, that's a beautiful question. Yeah. And I have personally tried, we tried with Shishibo for 7, so D equals 7 was our attempt. And for D equals 7, we failed, actually.
So I think the question assumes that D equals infinity might be easier.
Now, I know that there has been some approaches where you study the limit of conformal blocks in a very large number of dimensions, but one has to be very careful with that limit. And I know the subtleties are a bit technical, but one could basically write down the Bootstrap equations and just take a limit where D is very large in the conformal blocks, and you find some obstructions. But it's not clear that the obstructions are like real obstructions or they are there because of subtleties in taking that limit.
But, yeah.
We know it is true.
Well, we think it's true.
Yeah. Well, we could bet. But.
Right. But then you should be able to prove it.
Sure, absolutely.
If the Bootstrap has any power, it should be able to prove things that we know are true. Yeah, then there was another interesting question, along the lines you were saying so, but I'll repeat it anyway. What are the prospects of ruling out, that a given ADS effective theory, so
yes.
it has low energy expansion of a ADS theory, has a UV completion using the Bootstrap?
Yeah, well, I mean, it boils down to more or less the strategies that I explained.
So let me open it to the audience. We have a few minutes for questions in direct response. Edward?
Well, it's sort of true that general relativity is the only answer to Einstein's question of reconciling gravity and reconciling Newtonian gravity with special relativity. But we don't consider that a satisfactory answer to what general relativity is. We're more interested in the principles and ideas that Einstein discovered in generalizing it.
Yeah.
So by analogy with that, I'm not certain we'd be satisfied with an answer to what is string theory, which said it was the only answer to some abstract question.
Fantastic, thank you. So actually, so I think the important point about this question is the following, actually. And it's that if this happens to be true, and there is actually a minimal set of general principles that leads to a unique solution of Bootstrap, then we have to go to these principles and study these principles. So actually, in these 3 slides, the thing that is most interesting, if it is true, is actually whether the fact that a set of general principles exist. And then we need to focus in these general principles. Maybe even if it is true, even the unique solution is not that interesting. But it's interesting that there is a set of principles such that the solution to Bootstrap, well, which I haven't said which is what is this for this case, is unique. So I fully agree with you, and I think if this happens to be true, probably the general principles that make this to happen will be more interesting than the solution itself.
Yeah. We might come back to this during the general discussion, I'm sure. Questions? Yes? Sandeep?
A simpler question, I think, than just asking about the size of compact dimensions is just to ask what's been done in ADS3, but for ADS4 and higher, namely, can you have a large central charge conformal field theory with just the stress tensor and then a huge gap in the spectrum? And how much can you bound that gap in terms of central charge? Okay, do you think we can make progress on that for ADS, for 3D CFTs or 4D CFTs?
Yeah, no, it's a wonderful question, and I think the answer is yes. If I had to sit down and start a computation to do that, at the moment I wouldn't know what is the best way to do this. But this is very much, it sounds very much like one question that Bootstrap should be able to answer. And yeah.
Okay, good. We'll perhaps come back to some of these issues later. And thanks again, Luis. Great talk. Thanks.